Now we're going to see how Einstein obtained the GR field equation. I'll just make a note. Uh, Remember we quote unquote derived the equation motion using the minimum substitution rule. Uh, but we cannot do that for a field equation because we don't have a field equation in special relativity for gravity. So there's no way by substitution we can derive GR field equation. So we have to start from basically from Newton and from the symmetry principle. So the first we're going to talk about how to arrive to call the Einstein curvature tensor by way of called Bianchi identity. Then we talk about Einstein field equation. Then we're going to show there's an alternative way you can derive the field equation in some ways much more elegantly, more systematically by the action principle. Okay. We're going to talk about Einstein tensor. We have already displayed the symmetry and the contraction of Riemann curvature tensor. In particular, we have a cyclic symmetry in which we have the Riemann you had one upper index fixed gamma, and the lower three indices lambda mu nu we cyclically permute. Okay, lambda mu nu, nu lambda mu, and mu nu lambda, and add them up equals 0. So this is cyclic symmetry. And also we talked about contraction of the Riemann tensor to Ricci tensor, Ricci scalar. Uh, Riemann tensor you contract once for the first and third index, and the Ricci scalar by contracting the Ricci tensor. Okay, and I would suggest that some linear combination of the Ricci tensor and Ricci scalar metric tensor together would form the correct geometric side of the GR field equation. But any linear combination do. So the question, what kind of constant A, how to fix the constant A? Okay. Uh, Basically, Einstein suggests we can use by using the energy momentum rule. Remember, in special relativity, we had an expression that the energy conservation can be expressed for a field system can be expressed as the full divergence of the energy momentum tensor vanishes, which of course becomes the covariant divergence of the which we say this T mu u must be covariant constant. Okay. Now, if the right-hand side, the field equation satisfies this condition, so the left-hand side, the geometric side, must also. So therefore, this linear combination must be such that also satisfy this covariant constancy requirement. And it turns out this requirement fixes the constant A to minus 1/2. Okay. So therefore, with A equal to minus a half, this the left hand this combination is called the Einstein tensor. And then the field equation for the Einstein tensor equal to proportional to T mu nu. Einstein struggled for a long time to impose this energy conservation. It turns out the most efficient way to obtain this is using the so-called Bianchi identity, which people discovered by many leading mathematicians worked on for a number of years afterwards to find this way. And so-called the Bianchi identity is the four derivative of the Riemann tensor with the last index fixed was the first two indices of the Riemann tensor fixed gamma alpha, then lambda mu nu cyclically permute. Okay, this is so-called the Bianchi identity. So what we're going to do, we can first derive the Bianchi identity, and then show using Bianchi identity we can find that this combination of Ricci tensor Ricci scalar has the covariant constancy condition. So again, well, start with something we call Jacobi identity. Jacobi identity is involved so-called double commutator. Okay, uh, this commutator was another, so it's double commutator, and with the indices are permuted. Okay, now this is nothing to do with covariant derivative. Any object A, B, C, if they don't commute, they satisfy the Jacobi identity, because we just you multiply out this. For example, the first line calls for the first double commutator, because double commutator is the lambda uh, uh, times the commutator, then commutator times the lambda, and then you work out the commutator again, so you get these four terms. So anyway, for each this factor, you get four terms. Then you look carefully. That's there. All the cancellation going on. This cancels this. This cancels this. So this has nothing to do with covariant derivative. Any object, three object A, B, C, if they don't commute, they will satisfy the Jacobi identity, and all equal to zero. Now we apply this Jacobi identity to acting on the vector. Okay, in this case I wrote down the covariant vector, and they didn't work it out. And what you find using the fact, remember we said a commutator covariant derivative acting on vector equal to reach Riemann curvature times vector A. If it's a vector with higher rank, for example, say rank 2, then each index there's a Riemann curvature factor, and for low indices there's a minus sign here. Okay, and apply this to one of the double commutator, we'll find this equal to. It's just some calculation. Double commutator is the commutator and followed by D, and the D followed by commutator, and then the commutator using the first is this. Okay, and this one is a double commutator acting on a tensor of two indices. So apply this equation, so it gets this relation. Then when this covariant derivative acting on the Riemann tensor term holding A fixed, or acting on A with Riemann tensor fixed, you get these two terms. But turns out this term just cancels this term, so therefore you get a simple expression here. Just one is covariant derivative acting on the Riemann tensor acting on some A, or the Riemann tensor multiply the covariant derivative acting on A. Now this is for one double commutator, and if we apply to all three of them, and the first type of term I can collect and put in here, the second type of term I can collect and put here, the three terms for each of them. Okay. Now we notice the second line. This is just the cyclic symmetry of Riemann tensor we talked about, so therefore it vanishes. So the second line vanishes. So in order to satisfy the equal to 0, so it must have the first line vanish, which is just the Bianchi identity. Okay. I just put the index up, gamma, that's the mix. So now we're going to use the Bianchi identity to find out the constant equal to A equal to -1 minus a half to give the Einstein tensor. So basically we're going to show that combination of Ricci tensor, Ricci scalar is covariant constant if by applying Bianchi identity contract 3 times. I explain what I mean by contract 3 times. Well, first we will contract this Bianchi identity once, which means we multiply by the inverse metric mu alpha. Because the metric is covariant constant, so therefore, as far as the covariant differential goes, the metric tensor is like a constant. So therefore, we can just push right across the covariant derivative. Okay. So therefore, we multiply the g mu alpha, push across the covariant derivative. I get contract mu alpha that should become the reach tensor. Okay, and work out that because 1, 2 is the minus sign. And same way, you get this become Ricci tensor. And this one is contraction between the covariant derivative index was the one, so nothing can do it. So I'll leave it there. Now I'm going to contract this equation one more time with the inverse metric G gamma nu. And when I do that, again, we can push across the covariant derivative. So this becomes G scalar. Again, this because the new index, so nothing I can do. And here I can contract the Ricci tensor to become, rather, Riemann tensor to become Ricci tensor R alpha A. So the effect of the last term, this two acting on the Ricci tensor, is just raising with the indices. Okay, so this becomes raised here. Okay, now new index here is a dummy index summed over, and this mu is also dummy. So I can change name whatever. So I can change the same name. I change mu index to new. So therefore these two terms are the same. So therefore this becomes +2. Okay. Now I'm going to contract one more time so I'll contract with one more time with this, and when contract, there's nothing can do, so there's just a G mu lambda here. But when I contract this time over the again becomes the which just raises, this time just raises in the lambda interest here. Okay, so therefore I have the covariant differentiation of twice of the Ricci tensor minus the Ricci scalar. And that's exactly, if I divide by 2 on both sides of the equation, that's exactly the Einstein tensor that we're claiming. Namely, this combination is covariant constant. Now it's rank 2 and symmetric, involving second derivative of the metric as well as the quadratic in the first derivative. That's exactly what we're looking for, the geometric field equation, to generalize the Newton's field equation with the appropriate symmetry condition imposed. So it was the symmetry principle and Newtonian limit tells me that this we say that this should have this kind of form, and now GR field equation must be a tensor equations, and the right hand side is symmetric and is covariant constant. So therefore, the left hand side, the geometric side here, must also have these properties. It must be a nonlinear second derivative of the metric. So therefore, at a rank 2 and covariant constant, the only candidate we have is this combination, Einstein tensor. So therefore, that's we arrived. So the G mu equal to kappa mu is the Einstein equation. Now, if we would take the Newtonian limit, just like we did the Newtonian limit for the equation motion, we'll find that it recovers the Newton's field equation, and we can then also identify this kappa is direct to Newton's constant, 8 pi g over c to the 4th. So this is the GI equation, the Einstein equation. And this is, we haven't talked about cosmology yet, but anyway, in cosmology, it turns out we need to add a term to the Einstein equation, and the reason we can do this because again, the metric tensor is covariant constant. So therefore, if I add this, I do not spoil the criteria over here. So this left hand still is covariant constant. Now, this is we basically follow the way Einstein accepted Bianchi identity, arrived at his field equation. Turns out there's another way, actually, based pioneered by David Hilbert. We can the same field equation, and now we're going to work with sourceless case. Okay, can be obtained more systematically by the principle of least actions. Okay, the action for a field instead of the time integral for the Lagrangian for a particle is a 4-dimensional integral of Lagrangian density. Okay, the density is so therefore involve a volume integral of the density give you the action. And the requirement of this to be minimized, uh, uh, we require the Lagrangian density and the differential volume to be invariant under the four-dimensional coordinate transformations, because so that the action is also invariant under general coordinate transformations. So it's natural that we're going to identify the Lagrangian density to reach a scalar, because so that has all the metric dependencies in it, and so that's the invariant Lagrangian density for the source-free gravity. Okay, so this script L is simply the Bianchi scalar. Now the tricky part for us now is that the invariant full volume differential. It's not just d4. It's not just dx0, dx1, dx2. Rather, the fourth dimension volume multiplied by the square root of minus of the determinant of the metric, and this g is to determine the metric. Okay, the reason this combination, only this combination, is invariant volume is remember when we make a coordinate transformation, dx4 to x prime involves Jacobian. Jacobians determine the transformation matrix. Okay, and also the metric is metric was rank 2, was too low indices. So therefore, when it transformed, involved two inverse transformations. So therefore, when you take to determine that transformation matrix, you find the transformed determinant is related to the original determinant by 1 over the Jacobian here, because the inverse metric, the inverse transformation matrix leads to a 1 over the Jacobian. Okay. So therefore, you find then this combination, you notice d4x prime give you 1 power Jacobian, and the square root g prime give you 2 power 1 over 2 powers, but square root, so just cancel the power. So therefore leads to this. So therefore you see the combination of the square root of minus g, and the reason minus, of course, we work the signature of minus 1 1 1 1, and so this combination is only this combination is invariant. So therefore, we want to derive the Geoffrey equation, or its Euler-Lagrange equation, obtained from minimizing the action. So now it's called Einstein-Hilbert action. And so the Lagrange density L is Ricci scalar, and the invariant volume involves square root of determinant of the metric. And if I write out the Ricci scalar as metric tensor contracting the Ricci tensor, so the R is just okay. So now we're going to derive the field equation through requiring this variation of this action is 0. So the variation equals 0. Now the variation of this gravitational action has 3 pieces. I can depend on the variation of the metric, depend on the variation of the Ricci scalar, or Ricci tensor, and the metric, the variation of the square root of the determinant of the metric. Okay. We'll first show that actually the variation of the Ricci tensor leads to 0. So this actually can be ignored. Remember, the Ricci Riemann tensors contract once to give a Ricci tensor. So here's the expression of Ricci tensor. And the variation of this quantity you can work out to be is a full divergence. Something can be written as okay, and the divergence have to work out to be the metric times the Christoffel symbol, and it's in this combination. But because it's full divergence, when you take the integral, it turns into a surface integral. And surface integral, you can, for a large surface, always vanish in the boundary. So therefore, this variation leads to nothing, just 0. So therefore, we can ignore the variation of the Ricci tensor. So only these 2 terms. And the non-trivial part is this part. Okay. So we call that variation of the metric determinant, square root metric. Well, it's easier to compute this one to diagonal. Okay, so it was G mu nu is only the diagonal element. Okay, and therefore the inverse metric is if this G11, this be 1 over G11, and G22 is 1 over G22, this for the inverse. So these are the metric, inverse metric written in diagonal form. Okay. So the determinant is simply the product of these diagonal elements. So therefore, so this is the determinant. So the variation of this determinant is going to be, this is a product, right? Your variation, you vary one term, you hold the other fixed. The variation of the one term, you divide that by the term, then multiply that term. But once you multiply the term, the remaining two together forms the determinant. So for example, if the two-dimensional case, the determinant is G1 and G22, your variation is you vary one holding the other fixed. Okay, and then you multiply G11 divided by G11, then become the determinant again. So therefore, this is so that's this. And this sum can be expressed as a multiplication of the inverse metric, since element is 1 over the. So therefore, uh, this sum here, okay, can be thought as as the product of the inverse metric, because which is 1 over times the variation of the metric. Okay. Now, since the product G mu itself, the variation equals 0, so therefore I can revert in written as the metric with variation of the inverse metric with a minus sign. Okay. So therefore, start from here, del G, but del G is written from here, okay? And so this is minus G squared, so it cancels one, so it gets square root 1 G, and have minus 1/2, and so, okay. So here I'm just take care of the fact that it's square root here, okay? So therefore, the variation of square root minus G is equal to this expression. Now, the metric matrices are symmetric. You can always diagonalize by coordinate transformations. Okay. So therefore, even though we derive this for diagonals metric, but that's true for general, because any metric is, you can always diagonal by similarity transformations. Okay. So now variation has this, remember this term vanishes. So I have the variation of the metric and the variation of the metric determinant. Okay, and the first time you do nothing, you factor out. So when this term substitute by here, okay, I will still have a square root of metric, and then of the inverse metric tends. So both terms now have this square root of the metric, the determinant metric, for default is already in there, and the variation of the inverse metric and the coefficient is this. Now this variation is 0, so that since these are arbitrary variations, the only way we can zero is the integrand equals 0, which is the field equation we're looking for. So this is a vacuum Einstein equation derived by principle of these actions. I just make 2 comments. If you had a cosmological constant, you can easily incorporate, and also if the T mu does not vanish, you can also easily find the interact with other sources by modify the Lagrange, adding proper terms in the Lagrange density. So all these go through. Okay, so non-trivial part is what I present here. So that's end of our discussion of tensor in GR, and we're going to go on to black holes and cosmology.